Our next speaker is Amanda Hsu. She'll be presenting how to synthesize quantum circuit optimizers. Please take it away.
Thank you. Yeah, hi everyone. I'm Amanda. I'm a PhD student at UW-Madison, and today I'm going to tell you about my PhD research. So to get us started, why do we even want to do quantum computing? Well, in the 80s, Feynman introduced this idea of using quantum computers to simulate quantum mechanics. And then in the 90s, we had these breakthrough algorithms, such as Shor's algorithm for factoring numbers and Grover's algorithms for search. And one day, we'd like to be able to do things like material discovery, probably more than factoring large numbers. But it's kind of unclear right now when we'll be able to achieve that. But nevertheless, we've been making steady progress. In the 2010s, we started to have hardware that is publicly available. And in the 2020s, we've had some error correction demonstrations to resolve some of the issues of this very noisy hardware. And so a broad question that my work aims to answer is how can automation accelerate this timeline between where we are now and to some point in the future where we can actually realize these algorithms. All right. And in particular, I explore this question by focusing on this problem on optimizing these programs. And the main reason why we need to do this is because the hardware is extremely unreliable. So a program for a quantum computer might look something like this. It's a pretty simple circuit. And the wires, the horizontal wires, represent our state, or qubits. And then these boxes and these vertical lines represent the operations that we can perform on a computer, and we call those gates. And then the way you read this diagram, which will show up later, is from left to right as time progresses. And the issue here is that each of these gates has some probability of failure, and so once enough of this builds up, when you read your results at the end, it's going to be indistinguishable from random noise. And so what a compiler might want to do, or an optimizer might want to do, is reduce the number of gates in a program so that we can reduce the noise that is introduced to our computation. And another important thing to point out here is that the longer our program runs, the longer our qubits have to stay in the state that we want them to be in, and that's something that they don't like to do. But another objective is maybe you just want to focus on reducing these 2-qubit gates because they have an order of magnitude higher failure rate. And then we also have, when we have error correction, these rotations on the z-axis by a particular angle, which are called t-gates, are going to be hard to do fault tolerantly. So our objective shifts a little bit, and we want to really focus on reducing those, and 2-qubit gates are secondary. But let's say I have a way to optimize this program, this particular one. The problem is that it's not going to be executable on every device because it turns out that every device supports a different set of native basis gates. And we have a lot of different options in terms of hardware, and they each have their own way of implementing this idea of a qubit physically. And so they each support their own instruction set, and as physicists and engineers work on improving the hardware, they also improve the gates. And so the supported gates for a particular hardware platform can also change over time. And we'd like to not have to rewrite our compiler every time the basis gate set changes. And if we just optimize in one intermediate representation that is just one gate set, once we translate to our target one, we may be losing out on some optimizations in that gate set. So the overarching question here is, can we automatically synthesize an optimizer that is both effective and correct, as we would like all our software to be? And to break this down, I'm going to present an optimizer as these two components. One is the set of optimizations that you're allowed to perform, and then the other is the algorithm that you use to schedule the application of these optimizations. And to characterize this landscape, I'm going to be separating it into the optimizations and algorithms that are handcrafted and ones that are more generic or synthesized. So in a sense, like a generic search algorithm is synthesizing a schedule for applying these optimizations. And just to give you an idea of what a handcrafted pass might look like, it's like this very specific and rigid schedule of optimization. Great. So I'm going to present a bunch of tools here. There's like a collection of academic tools as well as industrial toolkits. But the important thing is that all this existing work touches some region of handcraftedness, which is not going to be generic. And so the question is, can we have a tool that lies completely in this synthesized region? And so that's what the first work I'll be talking about aimed to solve. And it does this by synthesizing some optimizations and doesn't really focus so much on the scheduling algorithm portion. So then there's a question of like, what is the best scheduling algorithm given these optimizations that we synthesized? And there was some follow-up work that tried answering this with reinforcement learning. But then there's another distinction here, and it's the separation between optimizations that we're able to synthesize ahead of time, and then optimizations that we can synthesize while compiling a circuit. And so the next question is, if we use both of these, is the reinforcement learning still a good scheduling algorithm? And is this even a good idea to combine these in the first place? So I won't be getting into the details of this in this particular talk, but we'll see the high-level ideas. So yeah, the majority of this talk will focus on this work case. And the way that we do this is by synthesizing some optimizations. So what are the optimizations that we're trying to synthesize? Well, if you're familiar with classical compilers, the things that we're trying to synthesize are these things called rewrite rules. And you might be familiar with people optimizations from your introduction compiler class. And so what a rewrite rule is, very simple. It's just a pair of programs, a left-hand side and a right-hand side that you can rewrite to. And if these are equivalent, then we call that a rewrite rule. And the way that you apply these is that you can go through your program and find matches of the left-hand side and just simply substitute it with the right-hand side. And then you can optimize according to some objective. But for quantum programs, what does equivalence mean? It's very simple. The semantics of a quantum circuit, it can be represented as a unitary matrix. And if you don't know what a unitary matrix is, it's just a matrix that satisfies this definition here. And like the dimension here is going to be not great because exponential in the number of qubits. But we'll say that two circuits are equivalent just if their unitaries are exactly equivalent. And because this is an important subroutine into synthesizing these optimizations, I just want to give you an idea that this is not an easy thing to check. Even if you had access to a quantum computer, it would be difficult to do this. But all right, so what do these rewrite rules look like? We have a few different classes. The first is like the rules that help you cancel out gates. So intuitively, even if you had like a classical NOT gate, which is this X here, you would, like if you apply it twice in a row, that makes sense that that'd be equivalent to the identity. It's the same case here in the quantum setting. And we have a couple other rules for other gates that also tell you when you can cancel gates. And these are good because we're directly reducing our gate count. And another way we can reduce the gate count is by merging these rotation gates that are next to each other by taking one rotation by the sum of their angles. And then lastly, an important class of rewrite rules are ones that tell you how you can move gates across one another while preserving equivalence, because this is in general not going to hold. And you need to be able to do this in order to have any hope of having interesting optimizations, because otherwise the search would be very simple, because you would run out of gates to cancel at some point. Great. And I want to point out here that these rules are symbolic, like they're parameterized on these angles theta, and this equivalence holds for all values of theta. So checking equivalence is going to be tricky. And what we also want to do is be able to check this type of rule where this S in the middle is not only symbolic, or this circuit is not only symbolic because it has thetas, but this S could be any circuit. So you can think of it when you apply this rule as like a wild card on some subcircuit that satisfies a simple constraint on its semantics. And this is empirically a very important rule. And in previous work, it's been formulated, just like applied as a handcrafted preprocessing phase. Great. So the synthesis problem that we're addressing here is given some specification of the native basis gate set for a particular device and some bounds on the size of the rules that we want to synthesize, we want to output some provably correct rules. And so how might we go about this? Well, the naive algorithm would be to start off with no rules and then just enumerate all the circuits I can possibly have given this grammar and some bounds on the size. And then once I have this set of circuits, I'm looking for pairs because a rewrite rule has a left hand and a right hand side. And then if they're equivalent, then we'll add it to our rule set. But this is problematic because, as you might expect, the size of the circuits is going to blow up very quickly, even for small values of max qubits and max size. And then this verification task is going to be hard because our circuits are symbolic. So what does it even really mean? And then all of the expensive verification task is buried in this nested loop because we're looking for pairs of circuits. So it's not looking so great. So the overview of our approach is that we're going to take a symbolic circuit. We're going to have a procedure of representing its semantics as a polynomial. And why do we want to do this? Well, because then we'll introduce this data structure that makes it very easy to group polynomials into equivalence classes. And we call this the polynomial identity filter. And so I'm not going to get into the details of the first step of this in this talk because they require a lot of background on semantics of quantum circuits. But the second part is relies on this very cute and simple algorithm that is backed by this lemma called the short-stipple lemma for testing if two polynomials are equivalent. So what does this lemma say? Well, say I have two polynomials, and I want to see if they're equivalent. The very simplest thing you might think of is just to sample some values from a finite subset of the domain uniformly and independently. And then just instantiate your polynomials with what these values that you sample. And then once you do that, check if they evaluate to the same thing. And of course, if this check fails, then you know that your polynomials are definitely not equivalent. But what is the failure case here? Is that if they indeed were not equivalent, then the probability that this check says that they are is bounded by the max degree over the size of the domain that you sample from. And in practice, the degree of these polynomials is going to be very small, and you can make the domain that you sample from very large, like the 64-bit integers. So that's great. It gives us a high probability way of checking if two polynomials are equivalent, and circuits are polynomials, so it gives us a way of checking if two circuits are equivalent. So what does this mean in terms of our synthesis algorithm? It means that we can have, let's say, I'm on my last circuit that I've enumerated. I can turn it into a polynomial pk, and then just use the set of values that I've sampled in my polynomial identity filter, instantiate it, evaluate it, and then just insert it into this data structure according to the value that I get. So you can think of this as like a hash map where the keys are these values, and then the values are equivalence classes of circuits. And when you do this, there's a nice, you can just use the union bound to bound the probability that you have a wrong rewrite rule because this is a probabilistic test. And that's going to be at most k squared. If you have k circuits, it would be k squared times the probability of one of these tests failing. And so if I have, for example, like 10,000 circuits, and they have degree 10, and I sample from 64-bit integers, the probability of having one wrong rule is going to be at most 10 to the minus 11. So it's a very small failure rate, and you could repeat this test if you're interested in boosting that. So if we revisit our algorithm and look at where the improvement is, it's basically, we don't have this nested loop anymore. You just enumerate your circuits and insert it into this data structure. And so instead of having a quadratic algorithm, you just need to do a linear pass through all these circuits. And the nice thing is that we have this handcrafted optimization as a symbolic rule, and we have a way of representing its semantics and checking if they're equivalent. And so how this work is normally evaluated is that we have a set of benchmark circuits, and we see how different tools do on reducing some metric. In this case, we're looking at 2-qubit gate reduction because remember that they had an order of magnitude higher failure rate. And so for this particular device, we can synthesize an optimizer in 1.2 minutes. There ends up being like 700 rules, and the probability of failure here is 10 to the minus 17. And the way that you read this plot is any points above the dashed line are circuits that we reduce more gates, and the ones below is like we're underperforming, and then on the line is the tools are achieve the same reduction. So in this case, we're comparing against other state-of-the-art handcrafted optimizers. This box tool is like an academic work, and then these other two are industrial toolkits. And as you can see, we're doing pretty good here. And if we revisit our landscape, there was this funny tool that was touching all of these quadrants, and it also has a similar idea of trying to synthesize rules, but it includes some manual handcrafted preprocessing. And so when we compare against that tool, firstly, we're synthesizing these rewrite rules much faster. And then secondly, when we compare them head to head, we're about the same. And I like to point out that this class of circuits that we're not doing as well, it's because they're applying some handcrafted preprocessing that's at a higher level of abstraction than the rules that we're synthesizing. And that's going to come back in future work. All right, so rewrite rules seem pretty great, but they're relatively small patterns and they can be pretty myopic. So what can we do more? So you might remember at the beginning of the talk when I mentioned these optimizations that you can synthesize at compile time. So what is that? Well, firstly, yeah, rewrite rules are these optimizations that we're going to synthesize ahead of time. But at compile time, there's this notion of being able to resynthesize a circuit. And if you're familiar with program synthesis, this signature will look very familiar. We just have a program, and then we can extract a specification from that. Namely, like I can get its unitary matrix, and then just pass that to the synthesis algorithm, and it'll return a circuit that implements that specification. And so these two techniques they have complementary strengths. Firstly, rewrite rules are fast to apply because we can synthesize this database ahead of time, and it's very easy to just search for a pattern. But on the other hand, circuit resynthesis, like we're trying to solve this search over the space of circuits at runtime, and so that's going to be quite slow. But the thing is that rewrite rules are small patterns, so they're going to be limited in the number of gates that you can have in a rule, whereas resynthesis is not limited in this way. Essentially, because it relies on getting the specification in the form of the unitary matrix, as long as if you act on a small number of qubits, it doesn't matter how deep this circuit is. So you could resynthesize a very deep subcircuit. And then finally, rewrite rules preserve exact equivalence, and it's very difficult or impossible to approximate a rewrite rule. Whereas circuit resynthesis gives you a very natural way of approximating your output circuit, and this is something that is acceptable in quantum computing. And so prior work did include both of these, but it implemented it in these very coarse fixed passes. And so the question was, can we have a search algorithm that synergistically combines the strengths of both of these types of optimizations? And I won't be able to get into the details of the algorithm, but you can assume that the answer is yes. And compared to the first one that just uses rewrite rules and simple beam search, the blue here is like the percentage of the benchmark suite that the tool does better. And then the darker color is matching, and then it's never worse. And then the story extends to all these other state-of-the-art optimizers as well, importantly, one that uses some expensive hardware. So what's next? Well, this landscape, while it looks very complicated, actually only represents a small fraction of what the quantum software stack might look like for compiling a program. And actually, we might have extra steps like converting a high-level program into a high-level circuit before we get down to this low-level assembly. And then even below that, we need to run on error-corrected hardware. And so actually, this native basis gate set, it's going to be implemented using many more gates when you try to do it fault-tolerantly. And so there are things that we might like to synthesize, such as rewrites over these higher-level circuits, or synthesize some implementations for some fault-tolerant implementations for these operations. And the thing that this has in common is that we need to reason about circuit generating programs, and this is going to be a more difficult task than what we were looking at before, which is like these concrete small circuits. Great. And yeah, I just want to point out that all the work that we've done is open source in our compiler, and that's all I have. Thanks.